Okay, so section 5.6, basically we're looking at three laws of logarithms, how they can be used for problem solving and how they can be used to write a log of a multiple argument here in terms of logs with just single arguments. So three laws. First law is if you've got the log of a product, that's the addition of each of the two separate factors in your product. So log a of m times n is log a of m plus log a of n. And so we go from a product to a log of a quotient, and that's going to be the difference of two logs. That's log a of the numerator minus log a of the denominator. And then our third law of logarithms is if we have the log of an expression raised to an exponent, the exponent can be brought down front as a multiplicative factor, and so log base a of m to the n is n, that exponent, times log base a of m. Okay, so the first example here, suppose I'm asked to express log base a of 3x squared y to the 7th as a sum or difference of individual logarithms. Well, the first thing I'm going to do is look at this as a product. I can look at this as 3x squared times y to the 7th, so I might say this is going to be log base a of 3x squared plus log base a of y to the 7th. I then can look at that 3x squared again as a product and rewrite that as log base a of 3 plus log base a of x squared, and then tag along log base a of y to the 7th. And I then can go ahead and say, okay, I've got a single log base a of 3, plus, now I'm going to use my exponent law of logarithm rule, bring that 2 down front, 2 times log base a of x, and use the exponent rule again, plus 7 log base a of y. So I've expressed my original expression, my original logarithmic expression, as the sum or difference of logs of individual values in my argument. So how about a numerical example? Same instructions. Express log of base 10 of 40 cubed as the logarithm of a single value. So first thing I can do is simply use my exponential rule, bring that exponent down front, 3 times log base 10 of 40. Now at this point I can do a couple things. I can look and say, well, you know, I'm done. I've expressed this logarithm log as I've got 40 cubed and I've got just the 40, but I can break this down a little more and make that argument smaller, because that 40 is 4 times 10, and if I then were to use my law of multiplication, my multiplication rule, to write this as 3 times log base 10 of 4 plus log base 10 of 10, I then say that's 3 times log base 10 of 4 plus, now 10 to some power equals 10. Well, that power would be 1, so I then could rewrite this as 3 log base 10 of 4 plus 3. So again, I've made my argument as small as possible, starting off here with a 40 cubed. I've made that argument just to be a number between greater than 0 and less than 10. Okay, same instructions, express as a sum or difference of logarithms of single values. So first step I'll use is my quotient rule, quotient logarithm law. So this is going to be log base a of 3x squared minus log base a of 7y. Then for each of these I can use my product rule. So I can rewrite this as log base a of 3 plus log base a of x squared minus over here log base a of 7 plus log base a of y. So then I'm looking at log base a of 3 plus log base a, bring the 2 out front using my exponential rule, minus log base a of 7, distribute the negative the sign through properly, log base a of y. So now again I've expressed what was initially a nasty looking quotient up here as a sum or difference of logarithms of single valued arguments. So let's take a look at a proof of one of these laws of logarithms. Let's prove that the log of a product equals the log of the sum of your two factors in the product. Now I'm going to use just a base 10 here. We could use any base number we want, 2, 3, 8, t, but we'll use base 10 just to keep it easier. And so our setup is, let's let that log of the product equal x. And then let's also let it set up, say, log of a is some number n and log of b is some number n, and then use our exponential definition of logarithms to rewrite this. 10 to the m is a, and 10 to the n is b. Then we're just going to go ahead and make a substitution in. A is 10 to the m, so then we have log of 10 to the m times 10 to the n. We know no pure substitution, that's x. And we then say, okay, so this is then log of 10 to the m plus n equals x by our law of exponents. So then we ask ourselves, we have 10 to the x equals 10 to the m plus n. Therefore, and I'll just go that through again, 10 to the x equals 10 to the m plus n. 10 to the x equals 10 to the m plus n. That's using our definition of logarithm here, base to exponent equals result. Therefore, I then know that m plus n equals x. And if I come back up here then, what's m? M is log base a, log base 10 of a, and n is log base 10 of b. So therefore, substituting then, m is log of a, n is log of b, that equals x. And if x equals log of ab, and x equals log of a plus log of b, therefore log of a times b equals log of a plus log of b. So you want to study this a little bit, go through it slowly. The key was setting up that we set the expression that we want to try and break down, we've just called another variable, and then each of the expressions that we want in our output, we've set those equal to another value, and we've used our definitions or our laws of exponents to help simplify through. So for the second law of logarithms, that the log of a quotient equals the difference of log of numerator minus log of denominator. Again, you can go through and just pick a base that's convenient, 10, and we set it up the same way as we did for proving that the log of a product is equal to the sum of the log of each of the two factors. So your setup is let your log of a over b equal x, and then you want to get log a equals something, log b equals something, use and rewrite exponentially. Then you're going to substitute back in, and you're going to follow the same procedure that we did for the log of the product being the sum of the logs of the two factors. So I'll let you do that on your own. Make sure you can do it. Okay, for our third law of logarithms, that is the log of a base, some base raised to an exponent, some expression with a base and an exponent, is the product of the exponent times the log of the base. Same setup as we've done for the previous two. Let's let our unsimplified expression here be equal to some other value, and we need to get a log m out of here, so let's let that be some other value. Rewrite exponentially, 10 to the y then equals m. Do a direct substitute in for m over here, so then this is going to be log of 10 to the y to the n equals x. And then I ask myself, well, definition of logarithms is a base, 10. 10 to the x equals 10 to the yn. Therefore, we have yn equals x. And therefore, What's x? X is log of m to the n. So then this is n times log m, making again that substitution right over here. Y is log of m, n times log of m equals x. And x, again from up above, we defined x to be log of m to the n. So I've shown then that log of m to the n equals n times log n, n times log m. Again, I'm not going to hold you responsible for these proofs. I think that you should see that, though, in the proofs that we're using laws of exponents to get the job done, and that should make sense because a logarithm is naught but an exponent. And you can also then play around with specific numbers and see why these laws make sense using real specific numbers. See the next slide. For example, let's consider you've got log of 10 cubed times 10 to the 5th. Right away we can say 10 cubed times 10 to the 5th is 10 to the 8th. And then I ask myself, 10 to some power equals 10 to the 8th. Answer is 8. Well, I could also use that law of logarithms here. This is a product, so write it as a sum of log of 10 cubed plus log of 10 to the 5th. Then go ahead and use your other, your exponential law of logarithms to bring the 3 and the 5 down front. 3 times log 10 plus 5 times log 10. 10 to some power equals 10, that's 1. 3 times 1. 10 to some power equals 10, that's 1. 5 times 1, 3 and 5 is 8. So either way, you can get to, again, we put in numbers here with the same base to make it pretty explanatory. Okay, last example, which doesn't really involve a law of logarithms. It involves more a definition of logarithms, but one that will crop up in calculus and will crop up definitely in probably SAT. They like to give you this one, the SAT subject test, and will show up in homework and tests, is suppose you have a base raised to some logarithmic expression, and the base in the logarithm matches the base in the exponent. And I want to simplify this. There's a couple ways to go about this. One way is to use your definition of logarithm and look at this and say, hey, I know that this expression up here is some log base a of y is some exponent. Let's call it question mark. So I know that a to the question mark is going to be y. Okay, remember this whole thing is an exponent. A logarithm is an exponent. What exponent is it? It's the exponent that when I raise base of a to it, I get an output of y. So this whole thing is that question mark. Now go ahead and look at your whole left side. I have a to that question mark. What's a to the question mark equal? A to the question mark equals y. And that's one way to look at it. Another way to look at it, which I kind of like looking at inverse functions, is to consider you have a to the log base a of y. You have two functions embedded here. Basically, you're looking at a function y equals a to the x, and you've got another function y equals log base a of x. And what do we know about these two functions? Those are inverse functions. One undoes the other. So what's my order of operations here? The order of operations is I'm going to do log base a of y. So I'm looking for some exponent. A to some exponent is going to equal y. And then what am I going to do with that input of y? Well, I've done the logarithmic function to it. Then I'm immediately going to exponentiate that. That would undo, that's going to undo my logarithm. And it's going to take me, if I started at y, did the logarithmic function, I now am then going to exponentiate, which is the inverse of my log function, and that's simply going to undo and take me right back to where I started from, which is y. So there are two ways to look at this kind of problem. So if you're given something like, 3 to the log base 3 of x to the 7th, and you're asked to simplify that, it's x to the 7th.